Hello and welcome to today's class. Today we're going to be looking at complex stress theory. Up until now we've considered stress pretty much one-dimensional. We've been talking about one-dimensional components being pulled in one direction. We can work out therefore stress is force over area. Obviously in real life that doesn't happen. We don't get one-dimensional components. We actually end up with three-dimensional components. What we're going to do today is be in the middle, and we're going to go for two-dimensional. We're going to consider two-dimensional components. So something which is loaded in two dimensions. So it's loaded in, let's say, the horizontal X direction and the vertical Y direction. How do those forces combine? What stresses are introduced into the component? And what plane do those stresses act on? So if we were to take a two-dimensional component and cut it at some plane, what stresses would we see on that plane? What direct stresses, what shear stresses? So what do I mean by previously we've talked about loading a one-dimensional component in one direction. So in a previous video, I was summarizing tensile testing, and in tensile testing, generally what we talk about is this sort of thing. So a simple one-dimensional component, typically a dog bone component when we're talking about metallic structures. So it tapers in the middle, so that we've got a gauge length here, we've got a circular cross section, we're applying a load. If that's a metal, if that's a steel, for example, we would expect to see a load extension graph looking something like this. Okay, so we've got this elastic region, we've got yield here, and we've got plastic deformation. Okay, so we've done a simple one-dimensional test, and from that we've got one number, the yield stress of that component which we're interested in, and we know below that it is elastic, and above that we're going to have this sort of plastic deformation. Okay, so what today's class is all about is where we say, okay, well, what happens now if we take this one-dimensional test? How can we use that to predict what's likely to happen in a three-dimensional environment? And actually, when we start doing that, things get very complicated very quickly. So we're going to take a step back, and actually we're going to look at this in two dimensions. So we're going to consider a two-dimensional component, not loaded in one direction, but loaded in the vertical Y direction and the horizontal X direction. And we want to consider what are the stresses which are introduced inside the component due to the fact that we've got these multiple loading directions. When is it likely to fail? That may be of interest to us. When is it likely to fail? And also, where is it likely to fail, and how is it likely to fail? So we're going to consider a few things. I'm going to put these PDFs onto Teams for you. The first thing that we're going to consider is a two-dimensional component. You can see we're loading that in X, so we've got a stress in the X direction, and we're loading that in Y. We've got a stress in the Y direction. You can see we're only loading that with normal stresses. Or direct stresses. Those stresses are perpendicular to the surface. There's no shear stresses. Shear stresses would be parallel to the surface. So a shear stress may be introduced if we're putting a circular shaft in torsion, for example. Here we're considering a piece of material being loaded in direct stress only. And what we're going to do is we're going to calculate what the direct stresses are internally within the component, and what the shear stresses are. There are shear stresses set up internally within the component, what those are, and also what the maximum shear stress is, for example. We'll then have a look at a component which is subject to shear stress only. And again, internally, there are direct stresses and shear stresses. Let's work out how we can calculate what those are. And then we'll look at a generalized 2D system, which is subjected to direct stresses and shear stresses. We can simply use this principle of superposition, actually, and just combine those previous two cases to this case here. So we can look at a general 2D stress system, and then we'll have a look at a couple of examples. Okay, this handout then goes on to talk about principal stresses, principal planes and so on. There's a second video which discusses that. So this is one of two videos, the first half of this handout, where we're talking about a generalized 2D stress system. What are the stresses on any plane within that system? This second video goes on and talks about principal stresses and principal planes. So let's consider the first case. Here we've got a two-dimensional piece of material. So let's, what do you mean by that? Here we've got our two-dimensional piece of material. We can see that that is, we'll mark this corner here as A. Look, this one is B, this one is C. Okay, there are direct loadings on that in two different directions. We have loading in the X direction, which is causing this direct stress here, sigma X. And if this is in equilibrium, we can have an equal and opposite load on the other side and equal and opposite stress on the other side, sigma X. So we've got loading in the X direction. We've also got loading in the Y direction. So let's mark that as pink. So we've got loading in this direction here, look, sigma Y. We've got equal and opposite loading. Again, this is in equilibrium, sigma Y in that direction. Okay, so where's our component shown in blue there? We've marked it as ABC. This ABC, I guess this corner would be D. We've got direct loading in the horizontal X direction. So think about coordinate system. X is horizontal, Y is vertical. So we've got loading in the X direction. We've also got loading in the Y direction. This is sat in equilibrium. Now, if we were to draw a free body diagram of that, let's take a cut through the center of that. Let's consider this triangular element ABC. Okay, now that diagram's a bit messy, so I'm going to redraw that. And you can see I've redrawn that here, ABC. Okay, so there's my triangle. That plane AB is measured from the vertical by this angle theta. Look. Now we've got sigma X acting on plane AC. We've got sigma Y acting on plane BC. And because if this is going to be in equilibrium, we must have a direct stress, and we'll draw that arbitrarily away from the surface. Away from the surface is typically seen as positive, so we've got a positive stress, direct stress sigma X, sigma Y, sigma theta, sorry, and a positive shear stress, so shear stress acting down the plane. We've got a shear stress of tau theta. If we do any questions later on and those numbers are negative, we've assumed it's positive acting in that direction. So all of these derivations, we're assuming the stress is acting in that direction. If we do some examples and the numbers are negative, it just means it's acting in the other direction. Okay, same with our shear stress. We're going to assume it's acting down the plane. If later on we do an example and the shear stress happens to be negative, it just means it's acting up the plane. Okay, so we've drawn our free body diagram with our stresses. So we've got this element ABC, there's sigma X on plane AC, there's sigma Y on plane BC, there's tau theta and sigma theta on this plane AB, which is some angle theta from the vertical plane. Okay, now we're going to assume that this is unit thickness, so that in reality, obviously this would be 3 dimensions, but we're going to assume it's unit thickness so we can simplify it to 2 dimensions. And what do I mean by that? Obviously my element would look something like this. Okay, so we've got C, B, A. We've got some thickness. Okay, and I'm going to assume that that thickness there is of unit thickness, so that suddenly all of our equations reduce to 2 dimensions. Okay, so when we talk about stress here, we know stress is force over area. Stress equals force over area. Okay, in 1 dimension. So in this direction, sigma x stress is force over area. In this direction, sigma y stress is force over area. We know our stress is sigma x. So therefore, we can redraw this element now, but instead of putting stresses on there, we're going to redraw it with forces. We know that our forces are our stresses times by our area. If we know the stresses, the area of this plane here would be A times by C times by this unit thickness, 1. Okay, so we can reduce that to AC, AC sigma times by 1, AC sigma x times by 1. So there, we've got our plane. Look at this shown here. Now, force is due to sigma x, AC times by 1 times by sigma x, AC sigma x. So we can redraw this now, but instead of with stresses, let's redraw it with forces. And that's what this next diagram is showing us. So here we've got the same element, ABC, and we've got some plane AB, which has been cut some angle theta from the vertical, and we've redrawn that with forces. So instead of sigma x in this direction now, we've got AC sigma x. AC sigma x, it's on the plane AC, and the force due to sigma x is AC sigma x, AC sigma x. Okay, so we've got AC sigma x in that direction. So that is this plane here. Let's draw that in a bit more detail. So this plane, this force here, which is acting away from the surface, AC, is AC sigma x. AC sigma x. We've then got a plane acting, a force acting downwards, which is BC sigma y. That's the force on plane BC acting away from the plane BC. And then we've got another direct force acting away from the plane AB, which is AB sigma theta. AB sigma theta there, look. AB sigma theta. Now, in addition to that, potentially we've got a shear stress. We've marked that shear stress there as AB or theta, AB or theta. Okay, so this thing is sat in equilibrium. Okay, so what I want to do now is we're going to try and come up with an equation to tell us what sigma theta is. How do we calculate what sigma theta is? So we want to end up with an equation that says sigma theta equals something. And so in terms of ideally sigma x and sigma y, and also theta. So if we know externally, if we think back to our original example, if we've got a piece of material and we know what the external loading is, sigma x and sigma y is, and we know the plane with theta, we can tell you what the direct stress is and the shear stress is on that plane. Okay, so we've got our piece of material. We've chopped that through this plane here, some plane theta. If we know what the external loading is, AC, or sorry, sigma x and sigma y, if we know what the direct loading is on the outside of the plane, outside of the element, we can tell you what the direct stress is and any shear stresses internally within that material at some angle theta. So let's now take that, and in order to do that, we're going to, if this is sat in equilibrium, we are going to resolve those two forces. So if we want to consider sigma theta, we're just going to say the forces in this direction away from the plane are the forces in this direction away from the plane. So that's going to be made up of two components, two different forces. There is we've got this component here of this red force. Clearly, that is perpendicular to our plane. So we want to know what that force is, that component of that force. And secondly, we've got the component of our green force, which is perpendicular to that plane. So again, if we extend that back here, that would be perpendicular, wouldn't it? Okay, so we're going to say, well, we can write down an equation. If this is sat in equilibrium, and we know it's sat in equilibrium, we're talking about static equilibrium here, that yellow force is equal to this component of the red force, which is simply AC sigma x cos theta. We're going to move through the angle, so we do a little bit of trigonometry. So AC sigma x cos theta, AC sigma x cos theta, plus this component here, which would be BC sigma y sine theta. Again, a little bit of trig. So we've got AC sigma x cos theta plus BC sigma y sine theta is equal to AB sigma theta. Yeah, and that's what we've got there. So we've got AB sigma theta, AC sigma x cos theta plus BC sigma y sine theta. So AB sigma x, AB sigma theta, that's our gold force. So let's mark that. So that is, here, look, that's equal to AC sigma x cos theta, AC sigma x cos theta. That's this red component, the component of this red force. So that's equal to this term here, look, plus BC sigma y sine theta, BC sigma y sine theta. That's this green component. Okay, so we've got this red component and this green component that are equal to this yellow component. So there's my green component there. Now, so we're getting now, we've got an equation which has got sigma theta equals something. We've got sigma x and sigma y in there, and we've got our theta angle. However, we've got these lengths AB, AC, BC. We don't know what those are. Clearly, that's dependent on the geometry. We want to ideally come up with a component or come up with an equation which gets rid of those lengths, because we want to end up with an equation which is independent of length, and we can work out what those stresses are depending on the stresses acting on the outside of the component. So how are we going to do that? We need to try and get rid of these lengths AB, AC, and BC. And in order to do that, we're going to use a little bit of trigonometry. So let's consider our triangle. Let me redraw that. Here, we've got our piece of material which looks something like this. We've said that that is at some angle theta. This was A, this was B, and this was C, I think. Just check that. That is the right way around. AB, ABC, yeah. Okay. So we've got ABC. Okay, so we know from our trigonometry, SOHCAHTOA, or silly, I remember it as silly old Horace caught a herring trawling off Tasca. Okay, no, so SOHCAHTOA, or however you want to remember that. Okay, so we can say sine theta, so there's theta, sine theta, for example, therefore, would be opposite over hypotenuse. So sine theta would be BC over AB. Sine theta. Cos theta would be adjacent over hypotenuse. Cos theta would be adjacent. So cos theta is AC over AB. And tan theta would be opposite over adjacent. So tan theta would be BC over AB. Sorry, over AC. Okay, so we end up with those relationships there. So there you go. You can see I've written those out there. So cos theta, AC over AB, sine theta, BC over AB. Okay, so let's use those relationships now to get rid of these lengths, AB, AC, and BC. So we're at this equation here. We understand now we've got that from our field, which was in equilibrium. If we then divide through by AB, so we end up with an equation which says sigma theta equals something. We've got AC over AB, sigma x cos theta, plus BC over AB, sigma y sine theta. We need to divide all of those terms by AB. And then looking at our trigonometry, we know AC over AB, well, that's actually cos theta. We know that from here. Okay, and BC over AB is actually sine theta. Again, we know that from up here. Okay, so we would end up with, if we plug in cos theta into there, instead of writing AC over AB, we're going to write cos theta. We'd end up with cos theta sigma x cos theta. That's sigma x cos squared theta. That's that term there. Look, and then our green term, BC over AB. That's actually sine theta. So I can plug that in there. Look. So I'm going to end up with sine theta, sigma y sine theta. So that's the same as sigma y sine squared theta. Okay, so and now we're really getting there. We've got sigma theta equals something. We've got that in terms of the external stresses, sigma x and sigma y, and also the angle that we've cut this plane, theta. Okay, however, you typically won't see it written like that because you've got cos theta and sine theta in there. We can use a little bit of trig to replace that so that we've only got one cos theta or sine theta. Okay. Now, hopefully you can recall these relationships. I don't expect you to remember them particularly, but hopefully you've seen those before, and we understand how we would put those or where we would get those from. Okay, so we've got cos squared theta. So instead of writing cos squared theta now, I'm going to write this is half 1 plus cos 2 theta. And instead of writing sine squared theta, I'm going to write a half 1 minus cos 2 theta. And by doing that, I end up with an equation which has, instead of having cos theta and sine theta in it, it's just got cos theta in it. You can see it there, look. It's got cos 2 theta in it, sorry. Okay, and then we can expand those terms. We end up with that, and then we can factorize those. So this term here, look, is here. This term here is here. Now, sigma x cos 2 theta is there. And now sigma y cos 2 theta is there. So we'd end up with that relationship there. And that relationship there, that is the same as that relationship. Where are we? Subject to normal stress only, this relationship here. Okay, so sigma x equals a half, sigma theta equals a half sigma x plus sigma y plus a half sigma x minus sigma y cos 2 theta. So sigma theta, remember, is the stress on the plane, that's the direct stress at the plane internally within the material at some angle theta, and that's given by this relationship. So if you tell me what the stress in the x direction is and the stress in the y direction is, and also the angle that plane is cut at, I can tell you the direct stresses internally within that structure. Okay, so we've taken that there, we've drawn a free body diagram considering our forces. We've then resolved that perpendicular to the plane to get our direct stresses. We end up with this equation here for our direct stresses. What this handout then does, it goes through how we would work out the stresses parallel to the plane. And why would we do that? Well, before we looked at the stresses perpendicular to the plane, so we said this stress here was equal to this component AC sigma x cos theta plus this component here BC sigma y sine theta was equal to AB sigma theta. And we ended up with an equation which told us what sigma theta was. If we want to get an equation for tor theta, instead of resolving perpendicular to the plane AB, we're going to resolve parallel to the plane AB. So we end up with an equation with AB tor theta in it, and that's going to be equal to this component here, AC sigma x sine theta. That is going to be equal to this bit, AB sigma y, AB tor theta, and this bit here, BC sigma y cos theta. Okay, so by resolving parallel to the plane, we end up with an equation which tells me what tor theta is, and we deal with that in exactly the same way. Okay, so we consider the forces, the sum of the forces parallel to plane AB, we work those out. We get rid of those lengths AB, BC and AC in the same way we did before. We considered our trig here, and by doing that we get rid of those relationships. BC over AB is actually sine theta, AC over AB is actually cos theta, so we get rid of those, so we end up with that there. Again, we can recall this relationship here. Again, I wouldn't expect you to recall that off the top of your head, but hopefully you understand where that's come from. You've seen that before. So instead of having an equation with sine theta and cos theta in it, we can end up with an equation with just with sine theta in it. So we plug those into there. We rearrange that. We end up with an equation with tor theta equals something. Okay. Tor theta equals a half sigma x minus sigma y sine 2 theta, and that's this relationship here. So what have we done there? We've got an equation now which tells me the shear stress internally within the material. If you tell me what the direct stresses are, sigma x and sigma y on the outside of the material, and the plane which we've cut our free body diagram, I can tell you the shear stress is acting on that plane. So there's our first scenario, our elements subjected to normal stresses only. Now that then goes on and talks about elements subjected to shear stresses only. And I want you to try that now. And a normal element, an element subject to shear stress only. We do the same thing. There's our element. We cut our triangle ABC. We draw our free body diagram. We put our stresses onto that. We then convert our stresses into our forces. There we've got our forces. We then look at our two components. So to work out AB sigma theta, that is going to be this component here, and this component here. That's going to be equal to that component there, if it's in equilibrium. So therefore we can resolve that and we can get an equation for AB sigma theta, and then AB tor theta, this component here, is going to be equal to this component here. Sorry, that component's acting downwards, isn't it? So that component there and that component there is going to be equal to this component here, which is acting upwards. Okay, so again, we can resolve that parallel to the plane and work out an equation for AB tor theta. So we do that. We use a little bit of trig, same trig again to get rid of these lengths AC over AB, these ratios AC over AB and BC over AB, and we end up with this equation here. So this is the direct stress internally within the element, which is subjected to this shear stress, tor xy, at this plane theta. So if you tell me what theta is and you tell me what the external shear stress is on this element, I can tell you what the internal direct stress is within this element. We've worked out the direct stresses, say the shear stresses we would get by looking at the sum of the forces parallel to plane AB. So we'll look at the sum of our forces parallel to plane AB. There we've listed them. We've divided through by this length AB. We've got rid of that using our trig. We've ended up with an equation there with sine theta and cos theta in it. We've recalled this relationship to get rid of sine theta and cos theta. So we've only got cos theta in there. We end up with an equation which tells me what my shear stress is internally within that structure. So there's my element subjected to shear stress only. Internally, we would have direct stress given by that value. and shear stress given by that value. So we can consider two scenarios, well, we have considered two scenarios there. The first scenario, we've considered an element subjected to direct stress only, and I've gone through and shown you how we would calculate the direct stress internally within that structure. I then want you to have a look at the element subjected, or sorry, the shear stress associated with that loading condition. You can then go on and have a look at the element subjected to shear stress only, and have a look at the direct stress and the shear stress within that component. What this handout then says is, well, what happens now if we've got an element which is subjected to direct stress and shear stress? So here we've got an element, we've got direct stress and shear stress on that element. And what we can do now is we can simply combine those two equations. Okay, so our element subjected to direct stress only, our element subjected to direct stress only. Let's summarize these. So our element subjected to direct stress only, the direct stress internally is given by that. So sigma x half sigma x plus sigma y half sigma x minus sigma y cos 2 theta. Now looking at our generalized 2D stress system, that's this lot. So that component there is caused by the direct stress on this element. So internally we would have direct stress, we'd have this bit, that's caused by the direct stress externally on the element. And then the second thing that we considered, our element subjected to shear stress only, the direct stress internally was given by this, 4xy sine 2 theta. And there you can see, there it is, plus 2xy sine 2 theta. Okay, so when we've got a piece of material subjected to direct stress and shear stress, internally the direct stress would be made up of two components. The direct stress caused by the direct stress on the element, that is shown here in blue, we saw that earlier, and the direct stress caused by the shear stress externally on the component. That's shown by this green component here. So we've got two components. So this component is from the direct stress on the outside of the element. This component is from the shear stress on the outside of the element. Those combine to give us the direct stress internally within the structure. We can consider exactly the same thing with the shear stress. So when we had an element subjected to direct stress only, internally there was a shear stress, and that was given by this here, half sigma x minus sigma y sine 2 theta. And that is a half sigma x minus sigma y sine 2 theta there. So our generalized 2D stress system, our shear stress internally is made up of two components. The first component is the shear stress caused by the direct stress externally. Direct stress externally causes this amount of shear stress internally. However, there's another component. So the shear stress internally is also caused by the shear stress externally. So the shear stress externally and the shear stress externally causes this shear stress internally. So got this element subjected to shear stress. Internally there is a shear stress, and that is this tau theta equals minus tau xy cos 2 theta. And that is there, look, minus tau xy cos 2 theta. So there's two components. So we can combine those two components. So the shear stress, so in an element subjected to a direct into a generalized 2D stress system, which has got direct loading and shear loading. The shear stress internally is made up of two components. The first component, this red component, is the shear stress internally caused by the direct stress externally. And the second component, this pink component, is the shear stress caused by the shear stress externally. So we can simply combine those two, all those equations. So that's how we would consider a two-dimensional stress system. So we've considered an element subjected to normal stress only. We've considered an element subjected to shear stress only. We've worked out what the direct stresses and the shear stresses are internally caused by those two stress systems. And we've then used the principle of superposition to say, well, what happens now if we've got a two-dimensional stress system subjected to direct stresses and shear stresses externally? Internally, if you tell me the plane of interest, at some angle theta from the vertical, we can calculate what the direct stresses are and the shear stresses are internally within that element. Interestingly, when we were considering a element subjected to direct stress only, we saw this. Now, shear stress internally is given by that. Now, the maximum shear stress, the maximum value of this can be sine 2 theta. Remember, sine theta just goes +1 - 1 +1 - 1 +1 - 1. So the maximum that sine 2 theta can be is 1. And where does that occur at? Well, if we consider the handout here, okay, the maximum shear stress is when sine 2 theta is equal to 1. So sine 2 theta is equal to 1, i.e. 2 theta equals 90. Or, so because sine theta is 1, sine 90 is 1. So sine 2 theta must be equal to, well, 2 theta must be equal to 90. Therefore, theta must be 45 degrees. So our maximum shear stress is given by that, a half sigma x minus sigma y, because this value here is going to be 1, isn't it? Okay, now that occurs at 45 degrees. Now we see that if we do a simple tensile test on a ductile material, and it's known as a cup and cone failure. If I just Google that, cup and cone failure, okay, look at some images. Let's choose that on there, say. Okay, so we see a simple tensile test on a piece of ductile material, and our failure is going to look like something like that. Okay, now what we would see is that that surface there is actually at 45 degrees because that part has failed in shear. Although the material is being loaded direct only, it's being loaded in tensile. So we've got if it's loaded in this orientation, it'd be sigma x, but there is a shear stress internally. And we can see from this diagram here what would happen. That part would neck. We start to see failure. The crack starts to grow and propagate. And then at the edges, you can see there that that's at 45 degrees because that is a maximum. That's where the maximum shear stress would be internally within the material is at 45 degrees because that value sine 2 theta is equal to 1. So we've got our maximum shear stress. It occurs at 45 degrees. So if you imagine that image there in 3 dimensions, so let's rotate around that axis there, we would end up with this image here. Okay, we're going to end up with this specimen which is broken in a cup and cone failure. So we've got our cup here and we've got our cone here, and that surface there would be at 45 degrees. Okay, so we've looked at our elements subjected to normal stress only, subjected to shear stress only. We've combined those. We've come up with our generalized 2D stress system. We've come up with those equations there. Let's now actually have a look at an example, couple of examples, or an example using these equations. So you can see there, partway through this handout, we've not got some examples. So what are the normal and shear stresses on this plane AB? So here we've got a 2D stress system, and we've got direct stresses in X and Y. We've got shear stresses on tau XY, we've got this plane AB, and we're asked to calculate what are the normal and the shear stresses on that plane. So let's have a look at how we would do that. So if we have a look in this handout here, there are solutions to those questions. Let's have a look at those. Generalized 2D stress system, we've gone through that. Okay, so there's this example. Okay, so we've got our piece of material. Oh, sorry, that's example 2. No, they're out of order. Let's have a look at. Okay, example number 1. Okay, so we've got our direct stresses, and we've got our shear stresses, and we've got our plane. Okay, so what about direct stresses first of all? In the x direction, so all our stresses are in megapascals. We're told that in the question. So in the x direction, remember when we did the derivation, we assumed that the stresses were acting away from the surface, and those were we were assuming they were positive. So the fact that these are going in the other direction, they're compressive. It just means they're negative. Okay, so sigma x is minus 20. Okay, we assuming that's minus 20, so that we can use the equations. When we derive the equations, we assume they're acting away from the surface. The fact that they're acting towards the surface doesn't matter. It just means we'll put that minus sign in there. Okay, so sigma x is minus 20. Sigma y is 50. That is positive. That's acting away from the surface. So we've got 50 megapascals in terms of sigma y. Again, we need to think about our sign convention. We're asked to calculate the stresses on that plane, which is 40 degrees measured from the horizontal. Now, when we derived the equations, that plane was measured from the vertical. So if it's 40 degrees from the horizontal, clearly that is going to be 50 degrees from the vertical. Okay, so 40 plus 50 is obviously 90. So that angle there, when we derived the equations, we actually measured it from here, didn't we? We actually said theta was in that direction there. Okay, so theta is 50 degrees. We're going to use these equations that we came up with. And our shear stress, again, sign convention. With our shear stress example, we assumed on the top surface, the shear stress was acting from left to right. And we assume that was a positive shear stress. So it's positive on the top surface, traveling from left to right. Okay, when we look at this question, the shear stress on the top surface actually goes from right to left. Now that doesn't matter, it's just acting in the other direction. So we assume it's negative. Okay, so hence the shear stress is minus 30 megapascals because it's acting in the other direction to the equations that we derived. Okay, so if we do all of that, and that's the hard part of this question, is understanding what sigma x is, sigma y is, theta is, tau xy. Once we've got all of that, we can just take those numbers and plug those into the equations that we derived. So there's, if we're calculating the direct stress, we're going to use equation number 6 now, this one here, look. Okay, so sigma x equals that lot plus, so that component, remember, is the component caused by the direct stress. That component is the component caused by the shear stress. So my direct stress internally is made by that equation there. Equation number 6 is that one there. Okay, so we've taken our terms, our values, and we just plug those into those numbers. We're being consistent with our units. So if we put stress in as 20 megapascals into this equation, the answer is going to be in megapascals. Okay, so minus 20 is there, look, minus 20 is sigma x. Sigma x is minus 20. Sigma y is 50. Y is 50, so there's sigma y minus sigma y, so minus 50. Theta equals 50 degrees. 50 degrees, so 2 theta would be 100. 2 theta would be 100. and tau xy 30 minus 30 megapascals. So they're minus 30 megapascals. So if we simply calculate that, there's my answer, minus 8.5 megapascals. Now, what does that mean? Minus 8.5 megapascals. The fact it's minus just means in the questions or in the derivations, we assumed that that direct stress was acting away from the surface. The fact it's negative just means it's compressive on that surface, is actually acting towards that surface. And we would see a direct stress of 8.5 megapascals. Okay, and in order to calculate the shear stress, so that shear stress equation is this one here, equation number 7. So we're just going to take that equation there. There it is, look, that equation there, plug our numbers in, and we're going to get that. Again, that is, it's a negative number. So we assumed in the derivation of that equation that was acting down the slope. The fact it's negative just means it's acting up the slope. So we see this. Okay, so we see 8.5 megapascals. 8.5 megapascals is my direct stress, but it's negative, so therefore it's compressive. 8.5 megapascals, and my shear stress minus 40 megapascals. Again, it's negative, so therefore it's acting up the slopes. Minus 40 megapascals. Okay, so if we had this structure and we had 50 megapascals tensile in that direction and 20 megapascals compressive in that direction, at some plane at 50 degrees to the vertical, we would have a direct stress of 8.5 megapascals and a shear stress of 40 megapascals. Okay, so that's how we'd actually go about using this stuff. So it's not hard, but what that question really demonstrates is the usefulness of deriving these equations from first principles, because we understand the assumptions that we made in order to get these equations. For example, direct stress is assumed to be positive when it's tensile and negative when it's compressive. Shear stress on the outside of the element is considered to be positive when it's left to right and negative when it's right to left. Internally within the element, it's assumed to be positive when it's acting down the slope and negative when it's acting up the slope. So we can see how we would use those equations. So it's just a case of taking the numbers from the question, interpreting those, putting those in the format that we have assumed in the derivations of the question. So for example, theta is measured from the vertical plane, not from the horizontal plane. So we would work out what those values are and then just find the relevant question, the relevant equation, and plug those numbers in. This component here, these equations here, 6 and 7, actually we can use those for direct stress or shear stress only as well, because if shear stress is 0, that term is going to disappear and we end up with that equation there, that blue equation there, which is subjected to direct stress only. It's this blue equation here, isn't it? Because our shear stress is 0 in this part here. So our shear stress is 0, so that term disappears in that equation there, and we end up back to this equation here. Okay, so we can actually just use this equation for direct stress and this equation for shear stress. And if the shear stress is 0, this bit's going to disappear and this bit's going to disappear. And if the direct stress is 0, then this bit is going to disappear and this bit is going to disappear. And we just end up with the relevant equations. Okay, so what I want you to do is have a look at those questions. We've gone through question 1 together. There are 2 more questions there, questions 2 and question 3. Have a go at those. In the next class, like I say, we'll actually have a look at principal stresses and principal planes. Now, what are principal stresses and principal planes? Well, what we've done today is we've considered a 2-dimensional stress system, and we've been able to work out what the stress is on any plane of interest. However, as engineers, quite often it's not the stress on any plane of interest that's of interest to us, it's the maximum stress, and we want to compare that to the yield stress of the material, i.e. we want to know if our component is likely to fail. So our principal stresses are the maximum and minimum actually, but the maximum normal stress on the material internally, so that we can compare that to the yield stress to determine whether or not we're likely to see failure. Now, how are we going to do that? We're just going to use a little bit of differentiation. We're going to take the previous equation and differentiate that and equate that to 0. So if you're a little bit rusty in terms of differentiation, particularly differentiating these trigonometric terms, cos and sine, it might be worth you having a look at those, refreshing your memory before you watch that second video. Okay, so that's the plan for the next video. Principal stresses, we'll look at the maximum stresses internally within the material and the planes on which they act, the maximum principal planes. Okay, but that's for the next video, the second video. Until then, what we'll do, we'll have a look at those examples. If you've got any questions on any of the material that we've covered, looking at the generalized 2D stress system, or the elements subjected to direct stress only or shear stress only, let me know. Drop me an email or ask me in class when we meet, and we can go through this either face to face or online. But yeah, if you've got any questions, let me know. Until next time, I'll see you soon. Cheers. Bye bye.